So it's my pleasure to introduce today's chaos speaker, who's Dr. Kristen Corbosiero, who was kind enough to take the drive down from University at Albany, where she's an associate professor with tenure there in the Department of Atmospheric and Environmental Sciences. Just to give you a little bit of background on Kristen, she got her Bachelor of Science in Atmospheric Science at Cornell in 1997. She then went to Albany and did her master's and PhD, working with John Molinari. They're focusing a lot on tropical cyclone structure and evolution, especially in sheared environments, different types of environments. After getting her PhD in 2005, she went over to NCAR in the ASP, the Advanced Studies postdoc program, for a couple of years, and then made the trek over to the West Coast at UCLA, Los Angeles, where she was an assistant professor up to about 2011. Then Albany wanted her back so bad that she was recruited back to Albany in 2011, where she's been ever since here. A little bit more about her. She's an associate editor for Monthly Weather Review, and one of the reasons why is she won the Editor's Award back in 2010, so she has very good reviews. She's written over 25 papers, actually 30 papers or so, on tropical cyclone dynamics and structure. So she's an expert in this field. So much so, you may have saw her on MSNBC maybe this weekend, or what was it, Friday or Saturday?
Friday night, yeah.
Friday night with Chris Hayes, right?
Yep.
So anyhow, they tapped into her knowledge for Irma and so forth. So that's exciting. She's won awards as well. One fairly recent one is a Women in Science Award from the Ford Foundation there at Albany, which is great. So my pleasure to introduce Kristen. She's going to talk to us a little bit about lightning activity and the intensity changes with cyclones.
Great. Thank you, Brian. And thanks for having me here today and being flexible on my title of my talk. I was going to talk about some other work I do looking at secondary eye walls in hurricanes. But with the recent activity of both Harvey and Irma, I decided to switch things up and talk about lightning in hurricanes, which was the project I actually started a very long time ago with my master's degree and just keeps coming back. It's a topic I really like to talk about and do research in. That's what I'm going to talk about today. And I'd like to acknowledge my graduate student, Stephanie Stevenson. Most of the work you're going to see here is stuff that she's done as part of her PhD. And I'll talk a little bit more about her next adventure at the end of this talk, since she'll be moving to the National Hurricane Center soon, so she'll get to have an effect on operations. So the first thing I want to show you is a loop of Hurricane Harvey. So what you're seeing here is a loop that's over about 10 days as Harvey was just forming here in the Gulf of Mexico. So what you're seeing is satellite imagery from GOES, I always want to call it GOES-R, but now GOES 16, overlaid with lightning density. All right, so the warmer colors are going to be higher lightning density. So this loop goes through in times from when Harvey developed to when it was rapidly intensifying, and then when it makes landfall eventually in Texas. And what I want you to look at over this loop is sort of what's going on with the lightning and the storm. So I'm actually going to bring it back to the beginning here. Maybe. All right. So when Harvey was just sort of getting its act together here off in the Gulf of Mexico, you can see that there's lightning that eventually forms sort of near the center, where you see this big blow up of convection, and then you see it active lightning in a rain band. When the center starts to form, there's actually very little lightning, right? And then right at this time, there's a lot of lightning around the forming eye. That's about a time when Harvey had a little bit of a break in intensity. And then there's intermittent lightning. When you see the eye appear, there's almost no lightning in the core. Right before it starts to make landfall, you get some lightning again when the storm is intensifying again. So there seems to maybe be a correlation between the lightning and intensification, but it's sort of hard to tell. So we can look at another case. So this is Irma. This was on the 5th of September when Irma was a strong Category 3 hurricane, and it play again, please. And this is only about over an hour, and you can see that during this time there's a lot of active lightning in the eye wall of the storm. And so the NASA Sport group, which is the group that sort of puts together all of the preliminary imagery looking at the GOES satellite, they posted this loop on their Facebook page, and they included a note that said, "Note increasing lightning in the eye wall, signaling changes in intensity of the storm." All right, well, signaling intensity potentially changes, but what way? Are we intensifying? Are we weakening? That's pretty wishy-washy language. That, all right, well, some intensity changes are going to happen, but we don't know what way they're going to happen. And if we actually look at what did happen, this is sea level pressure or wind speed here on the vertical axes with time. And the time of the lightning is this purple bar here. And so you see that right about the time of this lightning that Irma had been rapidly intensifying, then it went through a little bit of a steady period, then there was this lightning outbreak, and then it rapidly intensified into a Category 5 hurricane. So in this case, it looked like this outbreak of lightning preceded this period of rapid intensification. Now later on in Irma's life cycle, so here's Irma again, about a day and a half later, where it's just north of Puerto Rico. Now we're overlaying lightning on top of IR imagery. And you can, if we loop this again, you can see a lot of active lightning sort of scattered all about the eye wall pretty symmetrically right near the center. So the National Hurricane Center took note of this, and in their discussion, their 11 p.m. discussion, they said considerable lightning activity has been noted in the eye wall of Irma, which research has shown sometimes to be a harbinger of weakening. All right, so NHC thinks that lightning in the eye wall sometimes means weakening, and NASA doesn't know what it means, but they know it means something. And in this case, in Irma, you can see again similar graphic that I showed you before, time along the bottom and intensity either in pressure or winds on the side. And this purple bar again is when the lightning activity was, and Irma did eventually start to weaken slightly over the next couple of days, but that had more to do with its interaction with Shear and Cuba than it had to do with actually lightning. So in a short term, the lightning did not signal weakening in Irma's case. So just based on what's coming out of NHC and what's coming out of NASA, we can see that there's a disagreement or an uncertainty about what lightning in the eye wall of a hurricane might actually be. So, but why are forecasters looking at lightning? So some work by Mark DeMaria, who works at the National Hurricane Center, has shown that lightning does have the potential to improve intensity forecasts. So Mark DeMaria's group runs a model, a statistical hurricane intensity model you may have heard called SHIPS. And what this model does is use various environmental and hurricane parameters, and it makes a statistical forecast of whether it thinks a hurricane is going to intensify or not. And in this model are things that we generally think of as being important in TC intensification, such as SSTs, ocean heat content, shear. But in this 2012 paper, they added lightning parameters into this model. So both inner core lightning, meaning usually within 100 kilometers of the center, and this outer rain band lightning. And what you can see here is that the lightning, and this is on the vertical axis, is just the discriminant weight, so how much each of these parameters are having a weight in their statistical model. And especially inner core lightning has the potential, or has as much weight in this model as divergence and vertical wind shear, which is kind of surprising because we know that shear is a pretty negative factor on TC intensity and a pretty strong correlation with intensity change, and it shows that at least in the Atlantic it could have as much weight as shear. All right, so forecasters are looking at lightning because these statistical forecasts show that it might be related to intensity change, but this doesn't tell us about what direction this is going in. Does lightning mean weakening or strengthening? And it turns out that in the literature, there's a lot of disagreement on whether lightning in the eye wall is going to mean intensification or weakening. So these are just a few of the papers that have sort of talked about lightning in the eye wall. A lot of storms in the Northwest Pacific have shown that lightning in the eye wall is generally associated with intensification. We're in the Atlantic. The paper by Mark DeMaria and this paper by Thomas has shown that eye wall lightning is generally associated with weakening, not strengthening. And in the middle is my PhD advisor who said, well, sometimes it might mean weakening and sometimes it might mean strengthening based on some other factors. Cecil and Zipser are kind of in that camp as well, but they're outside of these circles because they used a satellite-based product where these other papers looked at ground-based lightning networks, which I'll talk more about in a minute. So there's a lot of disagreement in the literature about what might happen. And specifically, this paper by Mark DiMaria sort of showed that, that at least in the Atlantic basin, that rapid weakening, if we have lightning in the eye wall, is much more common than rapid intensification. So what we're looking at here along the bottom is a radial interval, lightning density on the vertical axis, and then there are 3 bars in each radial group for rapid weakening RW. Average intensity change is the gray, and then rapid intensification is the black. And just concentrating on the 0 to 50 kilometer bin, because that has the highest flash densities here, it shows that rapid weakening is 3 times more likely, at least in this study, to follow a lightning outbreak in a TC than rapid intensification. So this study by Mark DiMaria looked at 10 years of lightning data in tropical cyclones. So this was a pretty robust signal that they were getting out here, that lightning in the core of the storm was associated with weakening. However, at about the same time that Mark was conducting this work, I had just started at Albany and was looking at some projects with lightning and hurricanes, and came across Hurricane Earl from 2010. So Earl was a really interesting storm because it had a lot of lightning, and it had a lightning burst in the core that preceded a time of rapid intensification. So along the bottom here is the time, the day of Earl's life cycle. We have wind speed in the red and pressure in the blue, and then the lightning density in both the 0 to 500 kilometers, and the green is the inner core, 0 to 100 kilometers in the bars. And there was, at the beginning, so Earl formed, and it was sort of undergoing this period of steady intensification until this really huge outbreak of lightning with over 800 strikes per hour late on the 28th of August. And you can see there's also a lot of lightning in the sort of the whole area of the storm, out to 500 kilometers, but this huge spike in the inner core was really what interested me, because from looking at a lot of lightning data in hurricanes over the years, I can tell you that 800 strikes is a lot of lightning. You'll see later that most storms maybe have 1, 2, maybe 5, but 800 is a ton of lightning for a TC. That's even respectable for like a supercell. So that was some exciting amount of lightning. So that was really interesting to me. And the fact that it was happening before this period of rapid intensification in the storm. So also note that this Earl was undergoing sort of steady intensification, and then this lightning outbreak happened, and then it underwent RI. Right? So maybe what the sort of intensification of the storm, what it's doing before lightning, is important to what happens after you have this outbreak of lightning. Something else that was really unique about Hurricane Earl is where this lightning outbreak was located. So what you're looking at here is IR satellite imagery for one time for 0Z on the 29th. So that's right when this lightning outbreak was happening. And this is overlaid with lightning flashes from the Worldwide Lightning Location Network, which is the network that I'm going to use that I'll talk about more in a second. The vertical wind shear direction was from the northeast at this time. So here's the center of Earl, and we've got range rings every 100 kilometers. So here's the burst of lightning. Here's the center of Earl in the green dot. So this burst of lightning, which is inside of 100 kilometers, is actually located up shear of the center. And my previous work has shown that that's highly unusual, that 90 to 95% of lightning strikes in hurricanes are usually down shear of the center. So the fact that this burst was happening up shear was extremely rare. And so we thought maybe that was the reason why this storm was doing the opposite of what the DiMaria study said it should be doing. Yeah?
Can the imagery distinguish between cloud to cloud, lightning burst, and cloud to sea?
So it cannot. So this lightning network that I'm using, which is the Worldwide Lightning Location Network, cannot distinguish between cloud to cloud and cloud to ground. However, it's a sort of very low frequency network, so cloud to ground flashes are usually stronger than inner cloud flashes, so it doesn't pick up most inner cloud. So most of what you see with the Woolen network, or WWLLN, is cloud to ground. All right, so the final thing that made Earl's lightning outbreak unique is that it was located very close to the center and inside the radius of maximum wind. So what I'm showing you here is the lightning in Earl. So this is over about 9 or 10 hours here, from 21 UTC on the 28th to 06 on the 29th. And it just shows how this lightning burst evolved or rotated around the center. And this is this figure is relative to the vertical wind shear direction. So now vertical wind shear is just been rotated up. These are 50-kilometer range rings here, and then actually that's not right. This is 50, that's 100, and that's 150. So I labeled it wrong. However, here's also the radius of maximum wind of the storm. So where the fastest winds are in the center or in the storm. And so you can see this lightning outbreak started to the left of the shear vector and rotated around to up shear, which is where I showed it to you here. So it's up shear of the center at this time. So where all these green dots here, so at 0Z it's up shear. So this was also one of the really cool things, that this lightning burst was very close to the center. And other previous research had shown that if you could get really strong convection close to the core and inside the radius of maximum winds, that you could really keep all the diabatic heating associated with this convection near the center, and it could have the most effect on intensity change. So Stephanie and I, and actually Mark DiMaria, because we worked in collaboration with him, came up with a few hypotheses that could sort of rectify sort of his study versus what we found in Earl. And what we decided to do was test some hypotheses about intensity change following an inner core lightning burst. All right, so we thought that there were sort of additional factors that were important rather than just we had a burst of lightning. So those factors that we wanted to test were the prior 24-hour intensity change, that what the storm was doing before the lightning outbreak was potentially important to what was going to happen after the outbreak. And we hypothesized that slowly intensifying storms were more likely to keep intensifying or intensify rapidly after the burst. We also hypothesized that the azimuthal burst location, so around the center, was important, and that maybe if the burst was up shear, that would be more likely to intensify. And then the third thing we wanted to test was the radial burst location, that how close this lightning was to the center was important, especially if it was inside the radius of maximum winds. So we decided to test all of these factors in a large set of storms in both the Atlantic and the Eastern Pacific over a 10-year period. So as I said, the lightning network that we're going to look at is the Worldwide Lightning Location Network, otherwise known as the WLIN. And the WLIN is a ground-based global lightning network, and it's a long-range network. The sensors, the locations of which were, this is back in 2013, pick up very low-frequency spherics or sound waves from lightning. So the sensors don't need to be really close to where the lightning is happening to detect the flash. You just need at least 3 sensors to pick up on these very low-frequency waves that bounce off the ionosphere a number of times. So this is what the sensors looked like in 2013. There were about 70 of them at that time, and it's been pretty stable since then. And as I mentioned, this is only basically a cloud-to-ground network. It does pick up some intercloud, but weakly. So you might wonder, well, all of these stations are located on ground. It's a ground-based network. So how well does it actually do over the open ocean? And so there was a study that was conducted by Radlowski and Shea back in 2013. They were looking at the detection efficiency, that's DE, of the WLIN network from 2009 to 2012. And they were comparing the WLIN versus the lightning imaging sensor, which was on the TRIM satellite that ran for many years. And so this is a sort of all over the Eastern Pacific and the Atlantic, and then a close-up on sort of the hurricane areas that we're going to look at. And you can see that the detection efficiency in the Eastern Pacific is pretty high, 25 to 50%. So you might not think that that's high, but that's actually pretty good for a global lightning network. And in the Atlantic, it's a little bit lower, but there are, it generally is above 20%. So the detection efficiency here is much lower than a network like the National Lightning Detection Network, which detects like 95% of flashes. However, work that I've done with my group shows that even though the WLIN isn't picking up on all flashes, there's a good proportionality between, it doesn't need to pick up all the flashes for you to get an idea of how much there is and where it's located. So we feel confident using the WLIN because they're very open about where their sensors are located. They've done verification studies. So we feel good using this network versus other networks where they don't tell us all the warts that go along with things. So we're also going to need some data about the TC and its environment. So we're going to use National Hurricane Center best track data mainly for the location and intensity of the storm, and we'll be using a wind-based intensity. We also need some information about the environment, so we need to know the vertical wind shear. We also want to know something about the sea surface temperature. So we're going to take these directly from SHIPS, which, as I said earlier, is the Statistical Hurricane Intensity Prediction Scheme. So these basically come out of the GFS. And then the final piece of the puzzle is to test the radial location. We need to know where the radius of maximum winds are. The only way that we get really good data about where the radius of maximum winds is located are through flight level data, so recon into hurricanes. So when I talk about this part of the work, I'm only going to be talking about Atlantic storms, because that's the only, we only fly into storms routinely now in the Atlantic. And you'll see that the sort of number of cases we have is much lower because we were very strict about having a flight that went through the storm within an hour of a lightning burst. So we really wanted to be very strict about what we were doing. All right, so just one more bit of business before we get to the results is our methodology. So how we're going to define these lightning bursts. So in the DeMaria study, they just said if there was any lightning, there could just be one flash, they counted that as lightning and then correlated that with intensity change. But since we were looking at Uro, which had this really huge outbreak of lightning, what we wanted to do was define an intercore lightning burst, a concentrated area of lightning. So after much back and forth and lots of false starts on defining a methodology, we went with something pretty simple, that we were just going to look at the hourly flash density on an 8 kilometer by 8 kilometer grid that was in the upper quartile of all TC hours with at least one flash. Okay, so this was the sort of what we decided was the best in the end, and this number comes out to be the huge staggering number of 0.02 flashes per kilometer squared per minute. All right, so even if you multiply that by 60 to get hour, I mean, we're talking like less than one flash here. Most storms have a lot more than that, in the mean value of about 20 to 50 flashes, but we're not talking exactly like supercell thunderstorms on the plains here. So you might be wondering, well, what's with this 8 kilometer by 8 kilometer grid business? Well, we use the 8 kilometer by 8 kilometer grid because this work was being funded by GOES-R, and the GOES-R is a geostationary lightning mapper, and the expected nadir resolution of that is 8 kilometers. So they're paying the bills, so you do what they're gonna basically look like in the end. And part of this work was sort of thinking about comparing the woolen to what the GLM was going to look like. So that's why, and this is the expected sort of coverage of the of GOES 16, or as it is right now. All right, so where are these lightning bursts located? So here are the lightning bursts in both the Eastern Pacific and the Atlantic, so just the density of the bursts. When we applied this methodology, there were 410 bursts in the East Pac and 443. This is between 2005 and 2014. All right, so really a good sample size of bursts. You can see in the East Pac that they're pretty much concentrated where we just have storms in the East Pac, where they're sort of very limited to the north because of colder sea surface temperatures and shear. So in the Eastern Pacific, the lightning happens over a much smaller range of SSTs because TCs happen over a smaller range of SSTs there. Where in the Atlantic, you can see that the bursts are much more spread out. They're not necessarily just confined to the deep tropics, and they occur over a broader range of sea surface temperatures. All right, so now getting into sort of the meat of the results here. I want you not to pay attention to the colors at first, so just pay attention to the gray bars on this figure. And this is just looking at what intensity storms the bursts happened in. So just paying attention to the gray bars. This is the intensity at the onset of the burst by tropical depression, tropical storm, and then the hurricane categories. So this is the frequency of those bursts on the left axis. So you can see that most bursts are occurring in non-hurricane TCs. All right, most of the bursts are occurring in these weaker systems, depressions and storms, which is not really that surprising by the way we think about tropical cyclones. As they develop a warm core, they transition from being more cape and buoyancy-driven convection to more neutral convection that would probably less favor charge separation we need for lightning. All right, so most of these bursts are happening in weaker systems. All right, now I want you to look at the colors, which are on here. And they are showing with the right axis the percentage of TCs that intensified in the red, remained steady in the black, and weakened after a burst. All right, so it's just saying what happened after that time per category. And you can see that the weaker TCs, so on this side, so the weaker TCs tend to remain steady or intensify much more than the stronger storms, and the stronger storms are much more likely to weaken if they have a burst of lightning. And that's a pretty consistent signature between the basins, that the blue line goes up as with intensity, so more are weakening, and the red line is going to go down. These lines don't continue to the really strong hurricanes because we didn't feel like that was a good idea because there are very few of them that have lightning bursts. So there does seem to be a signature in here that weaker TCs are more likely to strengthen when they have a lightning burst, when hurricanes are more likely to weaken. And this maybe isn't shocking because weaker TCs are farther from their maximum potential intensity, so they've got more room to intensify. And I should mention at this point that all of the storms, so we did a burst climatology, and then we refined that burst climatology to only storms that were in favorable environments. So only these 400 and whatever bursts that I mentioned here. So the original number in each of these categories was over 700, and then we hacked them off by only ones that were in favorable environments, meaning low shear, high SSTs. So we're really trying to isolate the effect of the lightning and not the effect of the environment. All right. So now getting into those hypotheses that we wanted to test. So with this one, just pay attention to the bars and not the squares at first. So this graph is going to test this prior intensity change. So if what was happening before the burst was important after the burst. So along the horizontal axis is the prior intensity change, whether the storm was weakening, steady, or intensifying before the burst. And then the bars tell you what was happening after the burst. And I should have mentioned this on the previous slide, but the East Pac is going to be on the left and North Atlantic is on the right. So if you just look at these bars, you see that if the storm was weakening before, well, it's pretty likely to stay weakening after, or maybe it'll be steady. If it was steady before, it's most likely to be steady after. And if it was intensifying before, it'll pretty much intensify after. So persistence seems to be the key here. That if the storm was doing one thing before the burst, it's probably going to be doing that same thing afterwards. But we wanted to test that against the climatology in the basin of storms that didn't have bursts. So that's what the So the squares are just the climatology of all TCs in the basin. So over that 10-year period, burst, no burst, whatever. And you see that in that case as well, if you look at the squares, that, if it was weakening before, weakening after. Steady before, steady after, intensifying before, intensifying after. Just this 24-hour intensity change. So it doesn't seem that burst cases are significantly different from the climatology, and they're not. We did some bootstrap sampling, and we did statistical testing of this, and so burst cases were not statistically significantly different from the climatology in the basin. So our first hypothesis doesn't really work out. It doesn't really seem like if we know what's going on before the burst, it tells us anything about what's going to happen after. Okay, so climatology and persistence seem to pretty win out here. Right, so our first hypothesis didn't really work out. All right, so what about our second hypothesis? So now what we're looking at is where this burst happened relative to the vertical wind shear. So now along the bottom, I have shear quadrants. So down shear right, down shear left, up shear right, and then frequency in the bars, and then what percentage intensified, weakened, and remained steady. So looking at this graph, we can see that the red bars are higher than the blue bars in every quadrant, right? So more TCs intensified than weakened with a burst in any quadrant. So if you have a burst anywhere around the storm is more likely to intensify than it is to weaken. However, we can't really say it's more likely to intensify than weaken, but it's not necessarily whether it's going to remain steady or whether it's going to intensify. That's a little bit harder to say here. And I should say that this fact that more TCs intensified than weakened was statistically significant. That's what these gray bars are. So that's statistically significant in every quadrant except for Well, actually, it's not significant in the eastern Pacific, except in the downshear right quadrant, but in the Atlantic, it's significant in all quadrants, that these gray bars between the blue and the red do not overlap. All right, so the Atlantic seems to have a little bit of a stronger signal here. But if you remember, what we really wanted to test here was if having bursts up shear was going to be important. And it turns out that if you just look at the downshear quadrants on the left versus the up shear on the right, that most bursts are occurring in the downshear quadrants. So this fits with my previous research that showed that like 90% of flashes happen downshear. And indeed, most of the bursts are happening downshear. And there's no statistically significant difference between what happens in terms of intensity change if the burst is up shear or down shear. So our second hypothesis also didn't really turn out to be all that exciting. But rest assured, number 3 is going to pay off. All right, so now the final piece that we wanted to test was the radial location. So now we're looking at intensity change of TCs. So the intensity change is in the dots relative to the radius of maximum wind. So here is the 24-hour intensity change in meters per second. So all the intensifying ones are up here, the weakening ones are down here. And this is scaled relative to the radius of maximum wind. So the radius of the burst R was divided by the radius of maximum wind. So if it was at the radius of maximum winds, it would be on this one line. Inside the radius of maximum wind is to the left, and outside is to the right. Now, if you recall, I told you that the number of cases we were going to look at was going to be much smaller here. So there were 400 and something bursts in the Atlantic, but we're only looking at 51 of those here, which is actually a pretty decent number. Meaning that there was either a NOAA or a U.S. Air Force flight that went into the storm within an hour of the burst 51 times out of that 400. So a smaller number, but still decent, right? And so I should also add that these gray bars here, so when this paper was going under review, so this paper is conditionally accepted at this point, but when it was in review, somebody noted that, well, there are small errors in the center position of tropical cyclones. And that small error in the position might change where your radius of maximum winds are. So these bars are basically random 0.2 degree errors in the NHC center that we added to this so that we could sort of see what the spread was in terms of maybe if there was a center position error. And the bars are larger in here because we're inside the radius of maximum wind, so it's going to scale up bigger. All right, so just a note here that there are 20 intensifying cases, 22 steady cases, and then 9 weakening cases. Not really sure why they didn't, there are so few flights into weakening storms. It could be because they're sort of at the end of their life cycle and we don't really care to fly into them anymore, but that's just sort of the way things broke out. So to look at this graph sort of to test the hypothesis that we wanted to make, so we were saying that anything inside or basically at the radius of maximum winds would intensify and anything outside would weaken. And you see that indeed there are many more cases that intensified with or remained steady with a convection in or a burst of lightning inside the radius of maximum winds, and very few cases that weakened. Looking outside the radius or just around the radius of maximum winds, where we had a burst that was basically just at or just outside, we get a number of weakening cases and a few intensifying cases, but it's about 50-50 here. But you might notice there are these cases here, these storms that have bursts of lightning that are appearing between, let's say, 2 and 3 times the radius of maximum winds, and these storms are intensifying. So what's going on with those cases? So it's kind of hard to know unless we actually look at the lightning density. So that's what these plots are going to show you. So now this is going to be the burst density composited over the number of bursts in each category, so weakening, steady, and intensifying. In these images, they've all been composited with respect to the vertical wind shear, so the shear is actually pointing to the right in these images. So the radius of maximum wind is in red, and this is 2 times the radius of maximum winds, 3 times the radius of maximum winds. So, and then the bursts, the number of flashes per kilometer squared per minute here in the colors. So if we start from left to right and look at the weakening cases, you see that most of the weakening cases have a maximum in lightning that's located outside the radius of maximum winds and up shear of the center, which is kind of interesting. So it kind of goes against what we thought in Earl. This one maximum that's inside the radius of maximum wind just came from one case. But it seems that most of the lightning is actually outside the radius of maximum winds. The steady cases, interestingly, have a lot of lightning in the core. They're sort of right at the radius of maximum winds and in the down shear left quadrant, which is very consistent with past research. And then, interestingly, a couple of things show up with the intensifying cases. So this graph on the right here. So the first is that intensifying TCs seem to have kind of symmetric lightning about the radius of maximum winds. So this is good because we want symmetric storms are much more likely to intensify than asymmetric storms. So that was a good thing to see. However, we also saw this band of lightning that was about at 3 times the radius of maximum winds that was down shear and down shear right of the center. So these intensifying TCs also have lightning at 2 to 3 times the radius of maximum winds down shear. And this down shear and down shear right signal is something that we also see very commonly in the climatology of TCs. And this is more representative of rain band lightning and is really not the eye wall. So that kind of explains what was going on in these storms. That here we're not picking up storms that are really associated with the core. They're more associated with rain bands. And interestingly, the second part of the Di Maria study is that outer core or outer rain band lightning is associated with intensification, which I don't have time to talk about today, but this is completely consistent with sort of what he found. All right, so I went through that kind of fast, but that's all right. So, so just to summarize here, we identified intercore lightning bursts in the North Atlantic and East Pacific using the Wooling network, and we did this over a 10-year period. And we tested several hypotheses about whether TCs would intensify or weaken after a burst of lightning. And we found that, contrary to what Di Maria found, that more TCs intensified than weakened 24 hours after a burst, probably because we were looking at bursts instead of just 1 or 2 random flashes. And it especially was true if the storms were sort of steady or already weakening prior to the burst. But we really didn't find a strong signal with the azimuthal location, and the strongest signal that comes out of this is that whether the lightning is inside or outside the radius of maximum wind appears to be the key component to understanding the relationship between the bursts and what happens in terms of intensity change. And this is perhaps not surprising, again, given other prior research that's shown that if we have strong updrafts inside the radius of maximum winds, we can concentrate the diabatic heating of the storm in the core. It's sort of trapped from inertially, by strong inertial stability in the core. We can't sort of radiate it away. So this would be the most likely sort of scenario where we would get intensification. So I mentioned that this work was partially funded by a GOES-R grant, and we were working with Mark Di Maria on this. So part of these GOES-R grants were to develop products that might be useful to forecasters. So as I mentioned, we were partially funded by this group, so we came up with sort of a prototype sample product that we thought might be useful to forecasters. And so what we would like to see, or what we thought would be useful, was if you took an IR brightness temperature image and you plotted the lightning density on top of that, along with the direction of vertical wind shear. So this is of Earl that I showed you earlier. So you would see the direction of wind shear. You would also have a plot of where the radius of maximum winds were. This could come from flight level data. There are also some really nice satellite products that estimate this now. And this might be a good product that forecasters could use, because here we would see that the lightning is inside the radius of maximum winds. It's up shear of the center, which might mean more symmetric convection. And so this is the kind of product that we were thinking about that would be useful to the National Hurricane Center. And indeed, my student Stephanie, who's about to get her PhD, she's, as I mentioned, going to start working at the National Hurricane Center in 2 months. And her job will be to develop GOES-R products for hurricane forecasters. So something that she's been doing for research is completely going to be transferable now to what she's going to be doing. So hopefully when the GOES-R lightning data finally comes online, so we can look at pictures of lightning data, like I showed you the animations of in the beginning, but that data is not being released to the public yet, not for at least until 2 months from now. And so one of the first things that Stephanie will be doing is comparing the Woolen data to the GOES lightning mapper to see how well they do. So that is all I have for you today. Thank you.
Okay, time for questions.
Have you ever flown through a hurricane?
Not a hurricane, no. I did fly through a tropical storm once. When I was a grad student, I went down to Miami, so I did some work at the Hurricane Research Division. And when I was there, there was a very sad and weak tropical storm that I flew into. So it was not that exciting. But I'm hoping now that I'm going to have a student who's like on the ground in Miami that she'll be able to get me on a flight into a hurricane.
Yeah, Dick.
So the ship's statistical model, that is when it ingested lightning as one of the independent variables. Does it assume that it's always strengthening?
No. So it's given the lightning as one of the variables, and what they found there is that the inner core lightning is associated with weakening, where outer core lightning is associated with strengthening. So we can understand there's some reasons to sort of think about why inner core lightning would be good for intensification. Outer core lightning, it doesn't really make a lot of sense about why that would be good for strengthening, in terms of that you might think that convection was robbing sort of inflow from the core. But in the paper by Mark DeMaria, he said that, okay, well, maybe if you have this lightning sort of outside, it just shows that the environment is really favorable. There's a lot of CAPE, a lot of moisture in the environment, so it's just sort of good for intensification. That looking at the outer core lightning is part of Stephanie's thesis, and so she's sort of finishing up that part now and trying to figure out exactly what the mechanisms are that if you have outer core lightning, why that would be good. But in ships, inner core lightning is bad and outer core lightning is good.
Just another question. So that's corresponds to an overall improvement in the skill of that model?
Right. So when they put the lightning parameters in, it was in their RII version, their rapid intensification index, sort of offshoot of ships. So they haven't incorporated it sort of in the general ships, but they have put it into the RII, and it does increase the accuracy, especially in the Atlantic. It's not as good in the Eastern Pacific, which there may be various reasons for, but it does seem to improve the rapid intensification forecasting.
Yeah, given the woolen detection rate, like 10 to 50%, within that, the strikes that are missed, are there known biases that could affect your results such that, well, it's more likely to miss strikes in some quadrant or at some reasonable distance?
So it preferentially sort of misses weak flashes, so stronger flashes, because these things bounce off the ionosphere multiple times before they get to the sensors. So it preferentially detects stronger flashes, which is why it preferentially detects cloud to ground. But there doesn't seem to be any quadrant bias. So several years ago, my student and I, when I was at UCLA, did a comparison between the National Lightning Detection Network and Woolen for storms that came close enough to the United States that we could look at the National Lightning Detection Network. And there were no biases that we found in those storms. And so it was a really nice study sort of verifying how much lightning the Woolen was detecting in TCs. And right, at that time it was about 10%, but that was, gosh, not quite 10 years ago now, but it was a while, and the Woolen has grown in sensors since then. So even though it's only detecting about, probably on a best day, 25%, it doesn't seem, because it has to, for the Woolen, 3 to 5 sensors have to pick up on a flash before it can sort of triangulate where that flash is. So it wouldn't be, the sensor should be sort of distributed around the storm, and they're far enough away that there shouldn't be any sort of regional or quadrant biases. The only bias is that it preferentially detects stronger flashes.
So I maybe missed this. For the initial analysis, how do you associate lightning strikes with the actual cyclones? Is it for the first general analysis? Do you do that with just a given radius maximum?
Yeah, so we use the NHC centers, and so we interpolate those to every hour, and then we just plot the lightning, and if the lightning is in within, so we look out to like 500 kilometers at first, and so if the lightning is within most TCs are not bigger than 500 kilometers in radius, and so that's associated with the TC. So that's sort of the first cut.
So to follow up then, so when you were doing the radial analysis, you mentioned the uncertainty a little bit in the location of the storm center.
Right.
And so you're associating your temporal resolution for the lightning is an hour?
No, so the lightning, yes, the lightning comes in at, it's like milliseconds so the lightning flashes are very well timed, but we decided to break it into hours because most bursts will last about an hour. But we have done it down to a minute.
But for the actual storm location, you're doing that, so that's generally 6 hours.
So it's 6 hours that we interpolate to hourly.
Okay, so have you tried to understand if there is maybe a little bias in this? Because if you have a really small storm that maybe has a radius maximum of 50 kilometers and it's moving 10, 15 miles per hour, you could end up where some of these storms are actually just to the left or to the right of the radius maximum in this plot, but not actually that the case, because over that 6 hour time span it could change speed.
Right. So that was sort of one of so on this paper we have co-authors from NHC. So it had to go through an internal review there, and that was one of the things that one of the internal reviewers sort of asked us to do. So we added this, and so we also looked at, instead of using the National Hurricane Centers, we used the HRD and Air Force actual centers, their center positions of the storms, which are much more accurate. And it doesn't change qualitatively, it doesn't change the results, it does slightly quantitatively, so that's why we just decided to add the 0.2 degree. And that was done sort of bootstrap for sampling 10,000 times, sort of adding these random errors, and so it didn't, basically we decided that was sort of the cleanest thing to do. But yeah, sort of the speed might change right in that 6 hours, and that's something I guess we don't really take into account that could be done.
So maybe I can follow up really quickly. Have you looked at, you have relatively small cases, but have you looked at like the spatial distribution, right? So within the North Atlantic, in the sense that is there more like, so if the storms that are maybe moving faster that are recurving, is there a different signature than a storm in the Gulf of Mexico that are recurving?
Right, so we haven't broken that down because there are distinct signatures, so that the sort of, not dirty little secret, but the thing about ships is that ships does really well in parts of the Atlantic Basin and really horribly in others, because the Atlantic is very heterogeneous in terms of its background. So that we haven't broken that out, but that's something we could certainly do with the larger, and you see that if you look at sort of the distribution of where these things occur across the basin. Maybe if my computer wants to be happy. It's up here, but you can see that the storms are, that's this one, that in the Atlantic they're much more spread out. So right, I'm not sure of those 51 that we looked at with the radius maximum winds, where those located, but they're obviously not going to be the ones out here because they don't usually routinely find these storms. So it would be interesting to look at that if there are different signatures in the basin.
Yes, so I'm wondering, for the Irma case, it was category 5, so from 1 to 5. Was there any difference in lightning activity from category 1 to 5?
I haven't seen the sort of, go back to Irma here, I haven't seen any of the flashes that occurred earlier than that. I've only sort of seen them from this time where it was already a category 3. But that's certainly something we could go back and look at. But I do seem to recall that Irma was a case that lightning outbreaks were associated either with steady intensity or intensification. Certainly at this time, and I believe at earlier times as well.
In the review at the start with the analysis on the most Pacific and Atlantic, it seems like in the most Pacific, the temperature has more like increasing over the intensifying cyclone than the Atlantic. Is there
So, I don't like to ever poo-poo anybody's work, but some of the work that's been done in the Western Pacific, the methodologies have been a little bit less constrained and sort of less rigorous in terms of associating intensification specifically to bursts of lightning, that they've used like one flash or associated with those in intensity change. But it does seem, our results sort of are the opposite of Mark D. Maria, and they're more in line with the Northwest Pacific. So it does seem that lightning data or that lightning bursts are generally associated with intensification, so it does more support the Western Pacific work. But some of those papers are a little bit older. They were done sort of in the, not old, but about 10 years ago now, so we'd like to redo them with a more complete data set to see if the same sort of signals sort of shake out now. So the planes get struck by lightning. I mean, commercial aircraft get struck by lightning all the time, and it happens. I mean, so what I will say is that these planes specifically, they have radar on board, and the pilots do not like to fly through really big thunderstorm complexes. So if there was a plane flying through here at this time, it would probably not fly through the northern part of the eye wall. It would fly east to west, but not directly north, because and in a very intense storm, the plane would not be flying too close to the ocean. So storms don't really fly below 600 millibars in storms this strong anymore. So, but there's never been an accident in one of these planes that have lost lives. So these planes get struck by lightning all the time.
So what I was curious, I mean, clearly you get lightning, you need charge separation, and you imagine you need convection, and you're suggesting eye wall. I'm wondering about the microphysical contribution and whether that explains some of the differences, because if you're glaciated in ice and you can get more efficient charge separation, or some priming or ice splintering and some of the processes that we know, does that, you hypothesize that may help explain this?
Right, I think that certainly could be the case, that back in the sort of the mid and late 80s, when they were sort of doing a lot of routine flights into hurricanes, that there was a group of people, including like Bob Howes and Black and Hallett, that were looking at the microphysical characteristics of the eye wall. And generally, there's not a lot of supercooled water. So for charge separation, you need to loft water droplets pretty high. You also need grapple. And so there's not a lot of that in the hurricane eye wall generally. And then recently with the NASA Global Hawks, they've been able to, and some of the DC-8 and the WB whatever 57, they've been able to take microphysical, they collect sort of the size or what the stuff looks like in the storm. So Stephanie has been looking at some of that, especially in some of the rain band regions.
Yeah, I would think farther away.
Yeah.
Eventually there's ice, right?
Right.
And further away, and if you're looking at bursts of lightning outside of maybe related to that.
Yeah, so those are things that are part of looking at this point.
John, you have a question?
I was going to talk about the physics of lightning as well, but those first two movie clips of Harvey and Irma, there seemed to be a frame when suddenly it was a flash over the strikes all over the whole area.
Oh,
Is that real?
That in Harvey, that was not real. I mean, so that's at the beginning of the Harvey loop. You see that? I think that's so it happens really. It's right there. I think that's just some kind of error in the data processing. So as I mentioned, so the GOES lightning mapper was launched last November, and so and it's one of the instruments that needs the most testing. So most of the data from GOES-R is now being released in terms of like the baseline imager, but the lightning is not even in beta testing yet, and it won't be in beta testing until November. So they're still working out some of this. I should mention, this is the first time that a lightning imager has been flown on a geostationary satellite. That lightning imagers like this were flown on. It's going to be flown on the space station soon, but they were flown on the TRIM satellite, which was polar orbiting, that only went over every location once per year or once per day. So this is the first time they've flown a geostationary lightning mapper. So they're trying to figure it out, what their signals mean and how best their post-processing goes along. So that's not a... Yeah, I'm sure that may... I mean, you do see it, but some of them are definitely not associated with deep clouds, so that's a little funky.
Maybe last question, Ryan.
Now all the pressure's on me. Have you looked at all at like the change in RMW relative to lightning burst? Because so what you're showing, and again, correct me if I'm wrong, but it was that with intensifying hurricanes, you're getting more of the lightning outside of the RMW, right? The outer bands.
Well, so with intensifying storms, there's a signal of getting lightning inside the RMW associated with like eye wall.
So there was the
Right, but then
but
then there are associated with the rain bands as well. There's usually a signal.
So what I guess I'm wondering, and again, I'm not at all an expert in TC dynamics, but is it that you're getting convection in the rain bands that sort of is eventually getting condensed, and the RMW grows, and then you're getting new again? You know what I'm saying? Like it's also a size increase in the storm?
Probably not. However, we have started looking at whether that lightning outside could be secondary eye wall forming. So that's something we're trying to confirm with microwave data now. We've got a really great microwave data set that we've just gotten available to us. So we're trying to look at that. That's one of the things that Mark DiMaria that hypothesized. And there have been papers that shown that these outer rain bands, that could generate some low-level potential vorticity that could be fluxed into the core. That's one of the other ways that it could be seen as being a positive. But really why this convection that's happening just outside the center, why that would be associated with intensification is something we're still really trying to play out and look at with NASA field campaign data to look at what the inflow pattern looks like. Is there a sort of difference in pressure across these bands that might slow inflow? So those are the kind of thing we're really trying to delve into the flight level data now and trying to connect the processes to the lightning.
Okay, well let's thank Kristen. As a reminder, we have lunch down the hall.